Module 2.2, Continuity. Objective 1, determine continuity and understand how to use limits to determine continuity of functions. Objective 2, determine the points or intervals of discontinuity and continuity. Objective 1, define continuity and understand how to use limits to determine continuity of functions. Definition of continuity. Continuity in a function exists if everywhere on the domain a limit exists. Remember from the last section that in order for a limit to exist, both the right-hand and left-hand limits must approach the same height or range. Number 2, the limit at these points everywhere on the domain must be equal to the range or height at this point. Remember also from the last section that even though the limit of a particular domain may approach the same value from left and right-hand sides, it did not necessarily mean that the range at that particular domain value was the same as the limit. We will illustrate this in upcoming examples. The informal definition of continuity: if you can trace your writing utensil over the function from left to right without having to pick up the utensil, then the function is continuous. Example 1. A function where the limit exists at all points in the domain and the functional value range at all those points are the same as the limit. If you'll notice that no matter where on the domain we choose, the limit will exist. In other words, the limit from the left and from the right will go to the same number. So there is no place where the pen or pencil has been picked up. Example 2, we're going to look at a function where the limit exists at all the points on the domain and the functional value exists everywhere on the domain. However, there is a place in which the limit and the functional value are not the same. If we'll look at the limit of this function as x approaches 2 from the left, so it's negative 2 from the left, it's negative 2 from the right, but the functional value of this is actually 0. So here the limit and the functional value are not the same. Let's look at example 3. Here we have a function where the limit does not exist at all the points of the domain. That automatically breaks rule 1 of continuity. Notice that as x approaches negative 2, here we have the function from the right-hand side is equal to 1. And here the limit from the left-hand side is going to be equal to 3. So notice that this limit does not exist. Therefore, this function cannot be continuous. Let's look at our next function, which is a piecewise function. Let's go ahead and draw the graph of it. Here, if we graph the function, notice that our important point decides when it changes is going to be 2. So at 2, this thing, from 2 back, it has a slope of 1/2. So I'm going to go down 1 and over 2. And that'll give this one. And at 2, this one starts at 4 instead of 3. So we have an open dot, and it heads in a slope of 3 over 1. And so that one's quite a bit steeper. So there's the graph of the function. Let's find f of 2. Well, f of 2, we're looking at 2, and that's where it would be equal. So we're going to use the top one. So that would be 1/2 times 2 plus the 2. So that would be 1 plus 2, so we would get 3. So the functional value is going to be 3. Let's look at the limit as x approaches 2. Well, if we look at it from the left, it would be equal to 3. But if we look at it as it comes from the positive side or the right, we're going to see that it goes to 4. So this one does not exist because the limit from the left and the right are not going to be equal to. And therefore, since the limit is not equal to, this is not going to be continuous. In example 5, we're going to look at a piecewise function. The first thing we need to do is graph f of x. Notice that all 3 of the stipulations are all looking around x and 2. So let's look at the top one. Here, if we put 2 in for the x value, that would give us our height is negative 3. So at negative 3, And this has a slope of -2. So our function should look like this. And notice that it is open dot right here. Okay, so at x equal 2, it'll be open dot. Okay, and in the second part, it says that our height is going to be 3. So that's just a dot. And then the last one is for all values of x or of the domain that are greater than 2. And this one is going to have a slope. So if we put at 2, it's going to have a value of 4. And so it's going to be open. And then we're going to rise 3 and run 1. And so it should look something like this. So there's our graph. This goes off. Okay. So now let's find f of 2. Well, f of 2 is obviously going to use the second stipulation. So that will give us 3. Let's find the limit of f of x as x approaches 2. Well, if it approaches 2 from the left-hand side, we're going to end up with a value of -4. If it approaches, or -3. If it approaches from the left-hand side like this, we're going to get -3. If it approaches from the right-hand side, we're going to get 4. So notice that the limit does not exist. And if it is asking if f of x is continuous at 2, that would be no, because the limit does not exist. So this would be not continuous. Objective 2, determine intervals of discontinuity or continuity. Let's take a look at this function. In the first stipulation, we got a piecewise function. In our first stipulation, for all the values of x that are less than 2, it has a slope of 1. So we've got, starts at 4, solid dot, and we're going to have rise 1, run 1. So it should look something like that. And for all the values that are greater than 2, which will be open dot, we're going to have, if you put 2 in there, there'll be 6. 6 minus, that will give us 4. So it's going to start right there, and it's going to be a little steeper because its rise over run is 3. So notice that here, the limit will exist everywhere, and the limit and the function value will be equal to each other. So even though we have one open interval, the other one filled in the space where the other one was open. So therefore, this will be continuous. And it is continuous everywhere. If we were to write this in interval notation, it would be from -infinity to infinity. Let's look at our second example and try to determine the intervals of discontinuity or continuity. Okay, let's take a look at the graph of this function. In the first function, or the top line, we're looking at all the values that are less than 2. Notice that this is going to be open interval because 2 is not included. And notice that it's going to have a slope of down 2 over 1. In the second stipulation of the piecewise function, we have at 2 that our value will be equal to 3. So we're going to just have a dot there for the second stipulation. And for the last stipulation, we're looking for all the values that are greater than x. So that's going to be an open dot. And if we put 2 in, 2 times 3 is 6, minus 2 will give us 4. So we're going to have an open dot here, and then it's going to rise 3 and run 1. So we should see something that looks like this. So notice here, we have a lot of continuous parts in this function. However, at x equal 2, we have a place where we have a break, and therefore we have a discontinuity. And our intervals of continuity would be from -infinity all the way to 2, union with 2 all the way to infinity. Notice that 2 is not included with the open interval notation. And the last function we're going to look at is a rational function. Notice that we have a restriction in the domain where x cannot be equal to 0. And so our function should have a vertical asymptote, and our function should look like this, and like this. Okay, And notice that this function is continuous all the way till it gets to 0, where we have a discontinuity at 0. And it is going to be continuous all the way from negative infinity to 0, and that's going to be union with 0 all the way to infinity. Once again, notice that we are using open interval notation because 0 would not be included because of the restriction.